Okay, we start now with chapter 4. In this chapter, we'll talk about number theory. Okay, so we will be talking about numbers, divisibility, greatest common divisor, and prime numbers. So first, let's start with the definition of what does it mean to say that A divides B. So when I want to say A divides B, first I want to make sure here that the number A is different than 0. Okay, so because I don't want to be dividing by by 0 at any point. So I say that A divides B if there exists an integer C such that B is equal to AC. And we use the following notation to say that A divides B. So for example, 3 divides 12. The reason is 3 divides 12 according to this definition is because there exists an integer C. Okay, and this C, so there exists C in Z such that 12 equal 3 multiplied by C, and we know that this C is equal to 4. So if I can find a number so that this number multiplied by A is equal to B, then I say that A divides B. Okay, now whenever A divides B, I say that A is a factor of B, or A is the divisor of B. Now remember that when you want to list factors or divisors of a number, let's say if you want to list the factors or divisors of 6, well, basically you're going to list any number that you can divide 6 with. So you can divide 6 by 1, you can divide 6 by 2, you can divide it by 3, and you can divide it by 6. These are all the factors of 6. In the previous example, I said that 3 divides 12. Okay, and we showed that because there exists a number C, and that C is 4, such that 12 is equal to 3 times 4. So in this case, I say that 3 is a factor of 12. Okay, or I say divisor. So factor, divisor are the same. Now clearly, if A divides B, then the fraction B over A is an integer. Again, let's refer to the example that I mentioned. I said that 3 divides 12. Okay, now when I say that 3 divides 12, that means, according to this, that 12 over 3 is an integer. And it's not hard to prove this in general, because if A divides B, what does this mean? This means that there exists C in Z such that B is equal to A multiplied by C. Now remember, in my definition I said that A is not equal to 0, so I can divide both sides by A. That means B over A is equal to C. Oh, what was C? C was an integer, so that's why I can say that B over A is an integer. So if A divides B, then B over A is always the fraction B over A is an integer. And if A does not divide B, then we simply write this. Okay, so for example, 5 does not divide 12 because I cannot find an integer such that 12 equal 5 times that number. A simple exercise here: determine whether 3 divides A and whether 3 divides 36. An easy test to do that is this. I know that if A divides B, I'm looking at the third property here. If A divides B, then B over A is an integer. Let's check. Is 8 over 3 is an integer? Okay, clearly no. So this means that 3 does not divide A. Now, is 36 over 3 an integer? Yes. So that means that 3 divides 36. Moreover, 3 divides 36 because I can find an integer C such that 36, so there exists C such that 36 equal 3C, and this C is actually 12. Okay. Now we're gonna list some properties here, like this is a theorem, but this contains properties of divisibility. We will try to prove them, okay? And you will see that these type of proofs are really common in the exercises. So you're gonna find lots of these things. We're saying here that if A divides B and if A divides C, then A divides the sum of these two numbers. Well, let's see. What does it mean to say A divides B? A divides B implies there exists, I don't want to use C here because it's already used, so I'm going to just come up with another letter. Let's say there exists K1 in Z, so there exists an integer such that B is equal to A multiplied K1. And when I say A divides C, that means, similarly, there exists some integer K2 in Z such that C is equal to A multiplied K2. This is what I have. So I'm just trying to write what I have using the definition of divisibility. My goal is to show that A divides B plus C. So my goal is to show that I can find some number, some integer, so that B plus C is that number multiplied by A. Now I'm looking at these two equations. If I want to see to look at B plus C, I can write it as AK1 plus A times K2. Okay, now I can see that I can factor out the A, so that's A multiplied by K1 plus K2. Okay, so that's what I want, because now I showed that B plus C is actually A multiplied by some number, and this number is an integer because it's the sum of two integers. So then B plus C is equal to A times K, where K is an integer Z. So we can call this K. Okay. So by the definition, this implies that A divides the number B plus C. So just writing the definition, try to connect the things together and you will be able to prove it. So the same thing will be true if I change this, for example, to minus. Okay, so that's gonna work because when I mean the proof is going to be the same, but you're going to have like K1 minus K2, and it's okay if you have negatives, okay, because in the definition I said that A divides B if there exists C in Z. I didn't say that C is positive. Here's another one. If A divides B, then A divides B times C for all integers C. Okay, so we try to do the same thing, starting from the definition. So here the proof of 2. When I say A divides B, that means there exists K or K1 in Z such that B is equal to A multiplied K1. Now I want to show that A divides BC. Okay, so I'm looking at this equation. I want to get BC, so the easiest thing to do is multiply C in each side. So then B multiplied by C is equal to A K1 multiplied by C. Okay, remember that I want to show that A divides BC, which means I want to show that BC is equal to A multiplied by some integer. Well, I can see it here because this is an integer in Z. I can call it K. So then BC is equal to A multiplied by K, where K belongs to Z. And by K here, I mean K1C. So as a result, I see that A divides B multiplied by C. So you can see that in these two proofs, I was using the direct proof. Now, if A divides B and B divides C, then A divides C. Similarly here, I start with this, A divides B, so that means that there exists K1 in Z, such that B equal K1 multiplied by A. And when I say B divides C, that means there exists K2 in Z, such that C equal B times K2 or K2 times B, doesn't matter. Okay. Now I want to show that A divides C. Well, let us substitute B, okay, because I know that B is equal to K1A by this. So this means that C is equal to K2 times K1A. Okay, well, K2 times K1 is actually an integer, so this is equal to some integer K. So C is equal to integer times A. From the definition of divisibility, I get A divides C. Okay, so these are really nice properties, and the proofs are easy, and you will use this technique for some other uh, for similar problems. Well, actually here I have a typo. That should be here: a to the power k divides b to the power k. Okay, so for that one, I'll leave it for you as an exercise. It's very similar to what we just did above. Um, you just need to maybe write the definition, raise both sides to the power k, and then everything's gonna follow. Okay, here's an exercise. Prove that if a and b are positive, okay, and a divides b, then a is smaller or equal to b. Okay, so if a and b are positive and a divides b, so since a divides b, then I can say the following, that there exists c in z, such that b is equal to a multiplied by c. Now I know one thing. I know that c is positive. Why c is positive? Because b and a are given to be positive. So c is positive. Okay? And because a times c are integers is equal to b, then it's clearly that a has to be less than or equal to b, because the uh, lowest value c can take is 1. Okay, and the largest value c can take is b in that case. Okay, so if c is equal to b, that's the largest value, then a is going to be equal to 1, and in that case it's going to be less than or equal to b. If c takes the, and that's the worst case scenario, if c is equal to just 1, then a is going to be equal to b. Okay. So this is going to imply that a is smaller than or equal to uh, b. Okay. Here's another exercise. We want to show that if a divides b, then if and only if ma divides mb, but here m is non-zero integer. Okay. So if a divides b, so here we have to do two directions. Let's start with the first direction. A divides b implies that there exists k in z such that b equal ka. I want to show that ma divides mb. Since m is non-zero, I can multiply both sides by m. So mb equal mka. Okay, now I want to show that ma divides mb, which means I want to show that mb is equal to ma times an integer. So using the associative property of multiplication, that's the same as, okay, so mb is equal to ma times some k, which is an integer. That's how we have defined it here. So this is clearly true. ma divides mb. Then I have to do the other direction. So starting with ma divides mb, that means there exists an integer k in z such that m multiplied by b is equal to ma multiplied by k. Okay, now my goal is to get a divides by b. So I want to get that b equal a times something. Can I divide by m? Well, yes, because m is non-zero. You can divide by any number as long as you know that the number is not equal to 0. So mb over m equal mak over m. Cancel the m, cancel the m. You end up with b equal a times k. And this is exactly the definition of a divides b. Okay? So here we proved the two directions for this exercise. Now the division algorithm. This is the same division procedure that you used to do in middle school. So if you want to divide, for example, so suppose that you want to divide, let's say 21 divided by 4. Okay, so you do this, you do here like 21 divided by 4. How many 4s you have in the 21? You have 5. 5 times 4 is 20. You subtract, you get 1. Okay, now that means what? That means as a result, this is my quotient, and the one that I got here is called the remainder. Okay, now 4 is called the divisor because you divide it by 4. I'm trying to divide by 4. 21 is called the dividend. Okay? And notice how do we write our answer? We say that 21, which is the dividend, it's the quotient times the divisor, so it's 5 multiplied by 4 plus what remains, plus the remainder. Okay, that's what we are trying to do here. So let a be an integer and let d be a positive integer. Here I want you to keep in mind one thing. Every time we want to divide by a number, we're dividing by a positive number. Now I'm dividing a by d. A could be negative. I say a is an integer here. Okay, but d has to be positive. So when I divide a by d, then there are unique integers. So you can't give me now a number other than 4 and 1 that will fit this equation. Keep in mind that the remainder has to be between 0 and 4, including 0, excluding 4. So including 0, excluding always the divisor. So we're saying here that there are unique integers, q and r. Q is the quotient, r is the remainder, such that the remainder is between 0, but it could be equal to 0, and strictly less than d. Because if the remainder is bigger than d, then you can keep dividing, such that a is equal to dq plus r. As you can see it here, a was 21, the d was actually 4, the r, the quotient was 5, so qd plus r, if I want just to make the same matching. Okay, and r was 1, which is between 0 and 4. So as I said, a is called the dividend, b is called the divisor, q is called the quotient, and r is called the remainder. So this is called the division algorithm. So the procedure that I showed you, and you maybe you've seen this not only with numbers, actually you've seen this maybe with in Math 100. We covered this with polynomials. You divide a polynomial by another polynomial. So what are the quotient and the remainder when 29 is divided by 4? So just perform the regular division here. 29 divided by 4. This is 6, 7. 7 times 4 is 28. Subtract, you get 1. When you stop, when you cannot divide anymore. Okay, so the quotient is 7 and the remainder is 1. So this is a notation that we will get used to. Consider the equation given from the division algorithm, a equal dq plus r. So this is the result of dividing a divided by d. So I get the quotient q and the remainder r. Now r, we will use the following notation: a modulo d, a mod d. So a mod d is the remainder of dividing a by d. A div d is the quotient of dividing a by d. Now keep in mind that r, your answer for r has to be between 0 and d. Okay, so the answer here should be between 0 and d. The answer here is, I mean, there is no restriction, so q can be negative sometimes. So we have to be careful about this. So if I want to go back a little bit for the example that I just did, okay, so I can see here that 29 mod 4 means what? This means the remainder of dividing 29 by 4. So 29 mod 4 is equal to 1. Okay, and 29 div 4, that's going to be equal to the quotient, which is 7, according to what we defined in the this slide. Okay. So quick exercise here, 24 mod 3. So we divided 24 by 3 and we are interested in the remainder. Okay, so if you divide 24 by 3, actually, the remainder is equal to 0 because 24, when you divide it by 3, that's equal to 8. 8 times 3 is 24. The remainder is equal to 0. Okay, so that means 24 mod 3 is equal to 0. And 24 div 3 is going to be equal to 8. You can try this 101 mod 3 as well. So you divide 101 by 3 and then you find the remainder. Okay. Now, negative 11 mod 3. So here, this is an interesting one because I want to divide a negative number by 3. Remember that negative 11 mod 3, so that's equal, when I divide negative 11 by 3, okay, I should get a quotient and a remainder. Okay, so we have quotient and remainder. And I do have restriction about the quotient, about the remainder. So this is going to be 3 multiplied by the quotient plus the remainder. Okay, well, let's see. If you divide negative 11 by 3, or 11 by 3, let's just take 11. If you divide 11 by 3, you're going to get 3. 3 times 3 is 9. And then, but you have to be careful here. You can't do negative 11 by 3 is, the quotient is not going to be negative 3. Here's why. Suppose that you plug in negative 3 here. So you're going to have negative 11 equal 3 multiplied by negative 3 plus r. Okay, so that means that negative 11 equal negative 9 plus r. Okay, so r is equal to negative 2. That's not possible because I know that r has to be between 0 and 3. So in this case, r can be either 0, 1, and 2. It can never be negative. Okay, so for this reason, when I divide by a negative, I take one less, meaning that instead of having minus 3 here, what I'm going to do is I'm going to put minus 4 and things will work out. So that's going to be a 3 multiplied by minus 4 plus r. So that means minus 11 equal negative 12 plus r. So then r is equal to 1. Okay, so negative 11 modulo 3 is equal to 1. Remember that the answer has to be positive here, and it has to be between 0 and 3 without 3 in this case. Okay. Now, this is an interesting remark that a mod d and a div d for some fixed d are functions on the set of integers. Okay. So this is like you have a function f defined from z to z. Okay. For every integer n, for example, f of n gives you n modulo d. For some d fixed, of course, d has to be positive. Okay, so this is a function. This defines a function. Okay, because, for example, if you divide any number by d, you cannot get 2 remainders. You'll only get 1 remainder. So each value is going to correspond to exactly 1 value. Okay, but we'll leave it as an exercise to identify whether it's 1-to-1 and whether it's onto. That's an interesting question. So this is another example when we are dividing a negative by some number. Okay, so again, here's how I do it. I know 17 divided by 4. I look at the positive one because we know how to divide using the Euclidean algorithm a positive by a number. When I do 17 divided by 4, my answer is going to be 4 as the quotient and the remainder is 1. Okay. So when I want to do negative 17 divided by 4, I say negative 17 equal 4 multiplied. I don't put 4, or I don't put negative 4, I put negative 5 plus a remainder. In this way, I guarantee, so I just go one less in the negative side. So in this way, I guarantee that r is going to be between 0, either 0, 1, 2, or 3, because this is the possible answer that I can have. So minus 17 is equal to minus 20 plus r. This means that r is equal to positive 3. Okay? So as a result, I know that minus 17 mod 4, which is the remainder. So that's the remainder of dividing minus 17 by 4 is equal to 3. And the quotient, minus 17 div 4, this gives me the quotient, which is minus 5. Okay, so that's how we answer the following question. Okay, so you can check it here. You can try these exercises. You can just do it the same way as I did the previous one. Okay, this is the solution. You can try them and then